rotational motion, and probably I also solve a problem from your section. So let me allow to share my screen first. Alright, can you see my screen, right? So one more thing, please guys speak up, someone voluntarily, otherwise I cannot understand. Sometime probably it happen actually when I'm in the middle of the lecture, I could be disconnected from the network. If you do not give me a response, then I will
Yeah,
be,
everything's fine.
yeah, that's fine. Sometime if I ask you, please respond promptly. Otherwise, because sometimes it's happen actually, I could be disconnected or you guys could be disconnected from that. Then it's not going to be effective actually. So that's why you should at least respond. That, yeah, everything is fine. Alright, so in the previous class, basically, I discussed about that rotational motion, and I also discuss a case. Actually, I give you an example. That way, I'm to repeat from there. Let's say, excuse me, I have a meter stick which can be rotated about this point. So it's a meter stick. That means its length is 1 meter actually. So what I am going to do actually, I'm going to release that meter stick from that point. So it's going to rotate about this point. So it's going to be the strike that wall is fixed to that wall actually. So if it strike the wall, then at what velocity is going to be the strike? That was the question actually, right? So because the thing is that if you release that this meter stick, it will be follow that circular path to strike that wall over here, because in middle of the portion you will find out that this would be that position of this meter stick. I'm just talking about the snapshot at that moment of this meter stick. You will find over here, and at a moment it's going to be that at the final moment it's going to strike that wall, right? It will be over here. The question was at what velocity is going to be strike the wall. That was the question. So what I did over here, I use that energy conservation law over here. So I write EI must be going to be that EF, right? Because it's rotating about that point. And I also give that moment of inertia of this meter stick about the center of mass. It should be 1 over 12 ml square, where m is the mass of this meter stick and L is the length. Fine. So if I want to find out that velocity, probably I could find out that velocity that using that formula V would be omega r, right? We know that this is the relation also between that linear speed to the angular speed. If that meter stick, if I release from that point, it's going to make a circular motion. If you find out that this is the portion of a circle, right, then I can say definitely it will be rotate about this point. If it is make a complete oscillation, definitely it will be a circular motion. So that's why at the point, this point has a velocity which is actually the v, and that velocity we can make it correlate with the angular velocity which is omega, right? If I have somehow can find out this angular velocity and also that r is simply the distance from here to here. It would be basically the L over here. R is the distance over here, right? This one actually r, which is simply the L, which is the length of this meter stick. So that means if somehow I can find out the angular velocity, then I'll be able to find out at what velocity is going to strike that uh, wall, right, by the meter stick. Alright, to find out that one, let's write down this energy conservation law. I can write down kinetic energy initial plus the potential energy initial must be equal to kinetic energy final plus the potential energy final, right? Now let's choose, this is my origin. I'm choosing this is my x-axis and this is my y-axis. if I choose this is my origin, then what happened, and I also release that system from the rest, then I can say my this kinetic energy, sorry, this kinetic energy is going to be the 0 over here, right? Because I release the system from the rest. I can also say that this potential energy is also going to be the 0 over here, right? Can you write that one? Because I choose this is my reference level actually. So with respect to that level, if you use that formula for the potential energy, which is mg is height is 0, so your potential energy would be the 0 over here. In that sense, we are saying that the potential energy is 0 over here. Fine. Now that final kinetic energy, when it's going to be strike over here, that one I can write. I should use the color. So I can write this is the 0 total energy, must be the kinetic energy. Since it's rotating, at the point is over here, it has only that rotational kinetic energy, right? It is rotational motion, not the rolling motion over here. So that's why I'll write it should be half of I omega square, that is that angular velocity, plus the potential energy is going to that should be mg minus L by 2. That should be the potential energy.
স্যার পটেনশিয়াল এনার্জিটা যে জিরো হয়েছে এটার মানে হাইটের লজিকটা ঠিক বুঝলাম না।
Acha, fine. So I choose this is my reference level, right? If it is the reference level, then what is the height of this meter stick with respect to that level?
জিরো।
That's why the potential energy is 0.
ও গট ইট গট ইট। ওকে ওকে, থ্যাংক ইউ স্যার।
Yes, is there any more question over here? Is there any more question? All right, if it is not,
নো
then
স্যার।
do you understand why it is this final potential energy minus g mg L by 2? Is that okay with you? Should I explain that one?
Yes, sir.
Then why not you are asking? You are hungry, then I am supposed to ask you, are you feeling hungry? Why don't you ask me, then why don't you explain this one, why this potential energy is minus mgl by 2? Come on guys, be responsible about yourself. Alright, so I take this is that, let's say, when this system actually we are going to consider the potential energy, we always consider that it should be considered from the center of mass of this object. Anything we define that potential energy, because we consider all the mass of a system will be concentrated at the center of mass, right? That's why we look for when the system actually the rotating or moving, it's always try to move about this through the center of mass, and that's why we consider that all the mass actually of a system will be concentrated at the center of mass. Fine. So if it is so, and this center of mass of this meter stick, which is would be at that L by 2, which is half of that rod, right, or the meter stick, which is L by 2 over here. When you release, that center of mass follow that path and is come over here, right? When you strike the wall, its position of center of mass would be over here, and that distance is also again L by 2. Right now it should be minus L by 2 because I choose this is my origin, right? So that's why I'm saying that this height is going to be the minus L by 2. Do you understand? Alright, so then I can write this would be a half of I omega square should be mg L by 2. Now what is the moment of inertia? Moment of inertia, I have to find out about this end, because that rod is rotating about this end, one end, But I give you the moment of inertia of a system about center of mass, which is this one, about that point. So I have to use that parallel axis theorem, right, to find out the center of mass of that system. Because I know that it should be 1/3 ml square, but if you forget about it, you can use that parallel axis theorem, which said that the moment of inertia of a system of any axis, it should be ICM plus md square. Since I'm going to find out one side, let's say this is left side or the right side, whatever you say, or any point, then it should be 1/12 ml square plus m into, if you say the d is minus L by 2 square, then you will find out this I is going to be basically, if you solve this one, it should be 1/3 ml square. Now plug it into those thing over here. It's going to be that half of I should be 1/3 ml square must be equal to mg L by 2. Oh, it's knocking me right now. Alright, so then I can drop this half. I can also drop one more L. Oh, there's one more omega square I forget about. And I can also drop this m. Then I will find out simply 1/3 L omega square would be the g, or I can simply find out this omega is going to be that 3g by L, 3g by L. So that's with that angular velocity. Alright, so if I know that angular velocity, then I'll be able to find out linear velocity or linear speed, which should be what would be that? I can write down this should be omega into r. So I find out omega, which is root over 3gl into L, right? So and L actually is 1 meter. Then if you plug in those value, actually it should be 3 into g. G is actually 9.8. I'm sorry. So I have to plug in g, actually the 9.8 over here. So 9.8 divided by 1 into 1. If you solve, then you will find out this should be basically this V is going to be that 5.42 meter per second. This will be basically that. Linear speed of that system. Alright, you understand this part?
Yes, sir.
Alright. Alright, let's think about a twisting force. We are going to talk about today twisting force, which is simply defined as the torque. Let's say you have an object, or even this case actually the meter is T. You are going to rotate about this point. Then certainly you have to apply some force on that system, right? If you want to rotate, then depend also where we apply that force. Depending on that force, it will be rotate or not. Let's say if you apply the force over here, then the system, this is the force. If you apply over here, then the system will try to move in that direction, right? We'll find out, let's say some second later, it will be probably over here. So that means it's going to make a rotation about this case. Fine, but if you apply a force, let's say over here, this is the force you are applying. Will it be rotate? Probably not. It's not going to rotate. Or if you apply the force over here at the rotational point, the system is also not going to rotate. So that's means depending on that point where you are applying the force, the system will be try to rotate. The force actually which is responsible to rotate a system known as actually the torque. You say the torque actually this one. It's a twisting force. Torque, that's why he's saying the twisting force. Torque generally we explain by the math equation. It should be that R cross F. Never write down F cross R. It's not the same thing. It's not the right definition of the torque. Torque should be R cross F, not F cross R. This would be the wrong. Fine. Now, what is R? R actually would be over here where you are applying the force from your rotational axis. That's defined actually that, or you can say it in another way that position of your force from your rotational axis. Fine. So, and remember this force, since it's a vector, you can find out it's a cross product. You will find out its magnitude should be r f sine theta, right? This is that you know that from the vector chapter actually. The theta is the angle between your force actually and your line joining these 2 points actually. Sometimes it's also called the lever arm actually. This R is said the lever arm. So that means this would be basically the angle between your force and your displacement. We say sometimes like the lever arm actually. So this is the arm. This will be the angle over here. Sometimes you will find out the situation. Let's say instead of applying the force in the perpendicular direction, I can apply making some angle. Say this is my R, and I'm apply the force over here, which is, so this is the point. I'm going to apply the force over here. Like this is the force F over here. This is my F. Now this time system will be also the rotate, but it will be rotate. Let's say you can find out that angle. This angle is will be over here, not this angle. Remember, this is the angle. This is the angle. This is the theta. Then I can find out the component of this force, which would be this one would be F sine theta, right? Due to that F sine theta, the system will be again trying to rotate. It will be trying to rotate in that direction. So that's why this theta is the angle between your R and actually your lever arm, the force and the lever arm actually say that this is the angle. Fine. I say depending on where we apply the force, depending on that situation actually that the system will be trying to rotate. Let's say in this case I apply over here. If I apply the force over here, the system is not going to rotate. Why? In that case, the torque is basically the 0 over here. How it becomes 0? If you ask me, I know this time the angle is 0 over here, right? Because your displacement in that direction and force is also that direction. They are in the same direction. They are parallel vectors. So that's why angle is 0. If the angle is 0, then the sine theta is actually the 0. So sine theta value is 0. That's why torque would be also the 0. If you apply the force over here, then also the torque on the system is 0. In that case, why? Because your R is 0. The lever arm actually the 0 over here. So that's why the torque would be basically the 0. So you can find out the direction of this torque actually. You can find out, you can use the actually the right hand rule. Using that one actually you can find out that direction of the torque.
Sir, why did the eta head go? Like RF sine theta, there was supposed to be an eta head, right?
It's a, yeah. So it has some direction. It will give you the direction of the torque. So let's say you have to use the right hand rule if you apply. So let's say the situation will look like, say this is my R vector and this is my F vector over here. I will extend that one. This will be my F and this is my R, right? This is the vector. Then I have to use the right hand rule. Let's say R and the F are in this plane, XY plane. If you say this is actually your X axis and this is actually the Y axis, that means X is towards the, sorry, R is towards the X axis and F is towards the Y axis, then the torque or the tau would be towards the positive Z axis, which is actually out of this plane. If you see this screen, actually your computer screen or laptop screen, whatever you say, that tau would be out of your screen over here. If the orientation is look like that, if this is the R and this is the actually that F, because I am applying the right hand rule, I say that you have to place your forefinger in the direction of the first vector, then you will be rotate your rest of the finger towards the second vector, then the thumb will give you the direction. That's why it will be basically out of the screen or out of that towards the Z axis actually over here. All right, do you understand this one?
Yes, sir, I do understand, but in real life, how is that relevant? Like, if we're pushing something on X and Y axis, we don't see the result coming out of Z axis, right?
But that's yeah.
Like
I'm
for a
coming to that
door.
point. That's not the
Yeah.
actually yours. Yeah, that's a very good point actually you raise over here. That's actually the rotational part. So when you apply that the direction of the torque and the rotation are not the same thing. So when you apply the force over here, it will be rotating in that direction, right? That's the direction of the rotation. That's not the direction of the torque actually. Due to that force, it is trying to rotate in that direction. That's the difference between over here. The torque actually there is a, you can say that is a actually that force which is actually that make that rotation actually. It's a twisting force. You will find out that that's a condition actually. We will also say that there is sometime we will also use that there's a direction. That's also convention they use. Say let's say if it is moved the counterclockwise, we say the torque is positive. It is moved to the clockwise direction, we'll say the torque would be negative also. We'll also follow that convention over here. The point you actually make and raise over here, basically you are saying about the direction of that system. You understand?
Yes, sir.
Alright, so that's why when you're going to calculate the torque, these two things are very important actually. Where you are applying the force and which direction you are applying that force. Depending on these 2 points, the system will be trying to rotate. Alright, so so let's say I have a system like that. 2 point mass is connected by a massless rod, and let's say this is actually that M1 and this is actually that M2. I want to rotate that system about this point. Let's say this is the point. For this point I want to rotate this one. So that's why I apply some force over here, which is actually that F. Due to that force, the system changes its orientation. Let's say at a certain time its position is look like that. So this is actually that M1 and this is actually that M2. It means that it's created some angular displacement at the center, right? Which is say that let's say this is the del theta, as well as is also travel some linear displacement. Let's say this is actually that S linear displacement, or I can say this is actually the arc of this circular track. Fine. I can define, let's say this is also that displacement or lever arm from this rotational point to the place of this force. I can make a relation with this parameter actually. You know that I can write down S divided by R should be the del theta, right? It's a definition. R divided by radius should be the angle is going to be created at the center. You know that. So then I can write down S should be basically R into del theta. I'm going to use this one. It will be helpful for me. So when I apply this force on the system makes a displacement, then I can say there will be some work done. By definition, we can write down this work should be F into S. This is the displacement, right? And this displacement, I will also say that that would be also the change of kinetic energy from work energy theorem. Right, I can write down this one. So work done on the system would be change of kinetic energy. So that means this work done F dot S should be also the del K over here. Fine. If it is so, I can write this F is equal to that del K. Can you write? Look at this. I just dropped this vector sign over here. Why? These two vector force and the displacement are in the same point in the every single point over here. This is your force, this is your displacement, and every single point. So that's why these two vectors are parallel vector. Then the angle would be 0. So that's why cos 0 actually the 1. If you write down F is cosine theta, theta is 0. So that will give you the 1. So that's why I write down this one. Fine. So I will use this equation over here. Let's do that in another case actually. These change of kinetic energy, I can write these change of kinetic energy, I should be write kinetic energy final, which is minus kinetic energy initial. That should be actually kinetic energy final means it's only the rotational kinetic energy because the system is rotating about that point. Its center of mass is not moving. So that's why I'll write down half of I omega square f minus half of I omega I square, right? Which is that only the simply the change of rotational kinetic energy over here, because it is only the rotational motion, not the rolling motion or not the translational motion at all. So I can factor out this half of I from there, then it will give me omega f square minus omega I square, right? Now this thing I'll be able to write from that law of when the system moves at a constant angular acceleration, then I can write omega f square would be equal to omega I square plus 2 alpha into del theta. Can I write this on? Right. It is exactly that linear motion v square equal to u square plus 2ax. Right now, since we are dealing with the rotational motion, so that's why I write down that equation in terms of rotation. This is the final angular velocity, this is the initial angular velocity, this is 2, this is the angular acceleration, and this is the angular displacement. From here, I'll be write down, rearrange this equation, omega f square minus omega I square, it should be 2 alpha into del theta. Then I'll plug in this thing over here. Let's write down. So del k is going to be that 2I into 2 alpha into del theta, or I can drop this 2 from here. Then I can write down simply this del k is going to be that I alpha into del theta. Right now I'm going to plug in this del k into this equation over here and also the value of s. Then I'll find out. Now I'm going to write down f is actually that del k, or f into s actually r into del theta, right? I find out initially this is actually s actually r into del theta. Then I can write down the del k actually I find out right now, which should be I alpha into del theta. Then drop this del theta from both sides. Then you will find out this fr is going to be that I alpha. Now what is fr or rf? I'm substitute write down rf over here. So this is actually the torque over here, right? rf, this would be the torque where angle is 90 degree, right? So that's I can write down. So torque actually that I alpha. In this case, look at this. Initially, the angle is 90 degrees, so that's why sin 90 actually the one. I can say that this is actually the torque acting on the system. Due to that torque, the system is rotating, and this equation is known as actually Newton's second law in terms of rotation, because it is analogous to the F equal to ma. I said in the case of rotational motion, we'll analogous moment of inertia actually the analogous to the mass, and alpha is analogous to the actually the a. So that's why I can say this is actually that Newton's second law in terms of rotation. We will find out this part actually. We have to use randomly this one. All right.
Sir, can you go a little bit upwards in the screen?
Sure. Is that okay?
Sir, I think the screen is not adjusted. It's still in the same place. Oh, okay, sir, okay.
Why are you asking for that one? You are writing it from your...
Sorry, sir, I couldn't hear you.
So why you are asking for this one? Are you copying it from?
Yes, sir, I'm copying it.
It doesn't record actually, because this is actually the proof. And one more thing, actually, I already recorded this session. I'll post it into the actually YouTube. You can access is that from there actually.
Oh, okay, sir.
You just pay attention what I'm going to say. These are the theory I develop. I have to use this one. So that's why I'm developing this part actually.
Okay, sir.
Alright guys, do one thing actually. Give your attendance. Just write your ID into the text box or chat box. Do it right now. Hurry up. Because we have 15 minutes. Please everyone write your ID. Yes, everyone write your ID. Does everyone write your ID? Because I'm going to count your attendance from this ID actually. Those who are giving your attendance. Akbar Kamal Roy, were you late? Where you are? It's supposed to be submitted within 1 second. Alright, so let's pay attention over here. Let's talk about actually that angular momentum of the system. Let's say I have a object which is any arbitrary shape of object actually. It's going to be rotate about this axis. It is rotating at an angular velocity omega. Then the total system is try to rotate is that direction, right? Then if I choose a point mass over here, let's say which is mi, that will be also rotating. It means that it has some linear speed in that direction, which is vi, and I also consider the location of this point mass from this rotational axis at a distance ri. If it is so, then I can find out that angular momentum of this point mass we can write down simply by this equation. Angular momentum we express by that quantity L. It should be L should be R cross pi. This is the definition of that angular momentum for a point mass. If you have a mass which is moving with a speed v, it has some linear momentum, is the p, then the angular momentum from this system would be simply that r cross p. And it's a vector, it has direction, you can find out the direction using the right hand rule. Let's say I want to find out the total angular momentum for this solid object or solid system actually. Then excuse me, I need to do a little bit more over here. I can write down this system is like say r cross m into vi, because I know the definition of mi. So definition of this linear momentum actually m into v, I just replace in that way. I could be rearrange little bit this equation because m is a scalar quantity. I can factor out this one by the properties of the vector, say ri into vi over here, right? Now what is the angle between these two vectors? Can anyone tell me what should be the angle between these two vectors?
So you can't really see the picture.
You cannot see the picture, all right. Can you see it right?
So 90 degree.
It should be 90 degree, exactly. It should be always, because we know that we have an idea when a system rotating in a circular track, there is a velocity. That velocity is always tangential to the path. and every time if you make a angle, this angle would be 90 degree always at any point, right? This angle is going to be 90 degree. At any location you find out this velocity would be tangential to the path. That means it also makes the angle over here. This is going to be the 90 degree. That's why this angle is 90 degree over here. And I can find out in that case the magnitude of this case. This magnitude would be in that case mi ri vi, right? Because sine 90 actually is the 1. So if you take the cross product ri vi sine theta, theta is 90, I'll find out simply ri vi. Alright, let's do one more case actually. I can also replace this one. This v actually I could be replaced by this omega r. Can make a relation with the linear speed to the angular speed. Since this omega is fixed, that means that total system with moving at the same angular velocity omega is said. That means every single point on this solid object has the same angular velocity, but it has a different linear velocity. So that's why I will write this should be vi omega ri. I do not use any index for omega because omega will be the same for every single point mass. I'll replace that part over here. So I'll write down this L is going to be that mi, sorry, vi should be write down omega into ri. Then I can write, so omega is, I can write down mi into ri square, right, from this case. Fine. So right now this is the angular momentum for this, only that point mass mi inside that object. Now if I want to find out that angular momentum for whole system or whole solid object, I'm going to simply is there any question of any of you? So I'm going to simply summation of that, or I can integrate this part. So I'll write down in the general form. I'll simply write down the total angular momentum. It should be simply I1 to n into Li. Let's say there is n particle into that object, then I'm going to sum all of them particle to find out the total angular momentum of the system. Then if I write, it should be I1 to n is going to be the omega mi ri, that is the value of Li. Then I can write down this simply, it should be omega summation I1 to n is going to be mi ri square, right? Can I write this one? Now what is this mi ri square? Can anyone tell me that one? What is this mi ri square? Hello?
Sir, the moment of inertia.
It's the moment of inertia, exactly. That's the moment of inertia of all the point mass over there. So this is going to be that L would be in that case omega I. So this is that known as actually that angular momentum for a system which has rotating at angular velocity, and its moment of inertia I would be throughout that rotational axis. Then we can find out this would be actually the angular momentum of this system. Alright. Alright, let's do one thing actually. We find out over here angular momentum of the system, we write down, which is actually that r cross p, right? That's the definition of the angular momentum for the point mass distribution. Let's say I'm going to write down this one. I'm going to make a relation with that torque to this angular momentum. I can rearrange this equation. P should be write down m into v, right? Or simply you can write down, you can factor out this m. Alright, it doesn't require over here. Now let's say if I take the derivative of this angular momentum dl over dt, what I will find over here, I will use that operator d over dt, right? It's a mathematical entity actually. You can write down the mv. So right now I'm going to use the uv formula over here. Since I'm taking the derivative of this term with respect to the t, I have to use the uv formula. First one, I will take dr over dt, keeping the second function intact, plus second time I will take the derivative of the second function keeping the first function intact, which is r over here. So I will simply write down, it should be m is a constant, I will factor out, it should be dv over dt, right? Alright, so then what I'm going to write is a dl over dt. In this case, what is dr over dt will give me? Rate of change of position with respect to time. What it will give you? Rate of change of position with respect to time. What it will give you? What this parameter?
Acceleration.
Velocity.
It's a
Sir,
velocity.
velocity.
Yes, velocity. Rate of position. This will be velocity. V into mv plus r into, this one will give you acceleration. Rate of change of velocity with respect to time. It should be that acceleration. Now I can write this one d over dt. I can factor out this. M is a scalar quantity, v cross p plus r cross m into a, basically the force, right? Now what will give you? V cross v will be what?
So 0.
It should be 0 because angle is 0, so that's why this is going to be the 0 over here. I can simply write down the 0 r cross f. Now what is r cross f?
Dark.
It's a torque, exactly. It's going to be that torque we write down. That's why if you want to change the angular momentum of a system, you have to apply some torque on the system. It look like exactly that linear momentum, which is in that case you write down. This is also, we write down general form actually, that net torque on the system would be del L over del T, which exactly we write down in the case of linear momentum. Net external force, that should be that del P over del T, right? And the same thing we can say that if the torque is 0 on the system, who is walking right now? Faria Sultana, we almost going to finish the class. Why are you late, Faria?
স্যার সরি স্যার আসলে আমি নোটিফিকেশন দেখিনি
You were supposed to know that you have a class.
স্যার মেবি আপনি বলছিলেন যে রাতের দিকে ক্লাস হবে কালকে তো অনেকে জিজ্ঞেস করছিল আপনাকে স্যার তখন তো কোনো টেক্সট দেননি
No. Who said I will take the class in the night? I will say that I will take that actually the quiz at the night, not in the class, because this is the scheduled class. This is not my special class. This is actually the university scheduled class I'm taking right now. All right, pay attention over here. So if I say that if the net external, only the torque, not the external. Torque is external over here, definitely. So if the net torque is 0, we'll say that this angular momentum of the system will be the 0. Rate of change of angular momentum, then we'll say it should be LF minus LI will be equal to the 0. Then I will say that simply Li should be that LF, which is also known as conservation of angular momentum. The angular momentum will be conserved only if the torque is 0. Alright, this is also known as conservation of angular momentum. The angular momentum will be conserved. Sometimes we can also write this equation in that form, because L I know that I omega, right? Then I supposed to write I omega I f into omega f. But simply the moment of inertia is not going to change, because unless you do not change the axis, then the moment of inertia sometimes is not going to change. If the axis is going to be the change, then the moment of inertia of the system will be going to be the change. Otherwise not, it will be remain same. That's why this is also known as conservation of the angular momentum of a system. If the external force is 0, then we say that actually that linear momentum will be conserved. But if the torque is 0, then the angular momentum will be conserved. And that's why it is also say that, let's say sometime, this is also known that condition for, if I say that net external force is 0, then the system must be actually that cannot be move its center of mass, but it can be rotated, right? Let's say I have a disc. If you say that net force is 0, then the system is not going to move its center of mass, but it can be rotated actually. But if I say the torque is 0 on the system, then it cannot be rotated actually also as well. That's why this is also called that static equilibrium of the system. This is also condition for static equilibrium. For static equilibrium, we say that when the force is 0, the system is equilibrium, but that's not the totally static. But in that case, the system can be rotated. But if you say that net force is 0 as well as the net torque is 0, then the system would be totally static. It cannot be moved at all, or it can be rotate at all. So that's why this is also condition for the static equilibrium. One is net force must be the 0. Second one is also the torque on the system will be the 0. Then it's said to be the totally static of the system. This is also condition for the static equilibrium of the system. How many minutes do I have?
Sir, 2 or 3 minutes.
1 minute.
1 minute? You guys become late. You come into the late. All right. So I already finished that theory part. I need to do 2 or 3 more problems from this chapter, especially three. I'll try to do that. Then I'll move to the next chapter actually, which is gravitation, which is interesting. Then we are going to meet in the next class is when? 26, right?
Yes, sir.
All right, that's great. So this is also the last class before your vacation. So all right. So is there any question over here?
স্যার আমার একটু সমস্যা আছে
Sure. Go ahead.
স্যার অ্যাকচুয়ালি আমি টর্কের পার্টটা একটু গোলাচ্ছিলাম মানে একদম ফার্স্টের দিকে যে টর্কটা বুঝছিলেন তখন
All right. So fine. So which part can you say is precisely which part I need to?
স্যার আই ক্যানট সি ইউর স্ক্রিন
Right now I stop the sharing.
এটা অনেক ভালো হতো যদি আপনি স্ক্রিনটা